Assalamu alaikum. Welcome to new lecture. This lecture is an advanced form of our previous lectures, where we describe the various kind of demodulation technique, modulation and demodulation technique. For example, FSK, ASK, QPSK. So in the previous schemes, we considered there are two possibilities. There are two signals. For example, in PSK or phase shift keying, there are it is 0 or it is 1, or the signal is corresponds to the phase 0 or phase pi. Now today, or the following lectures will be a very generalized form of the previous modulation technique, and we called it M array or M array phase shift keying. Probably you already know that PSK we already discussed. So that PSK was BPSK, binary. So in this lecture, is binary means 2, right? So in this lecture, this phase, the possibilities of phase shifting are m numbered. Okay. So this is a M array phase shifting. Now this is very generalized concept of this BPSK, right? This is a very generalized concept of PSK. Instead of BPSK, it could be generalized. The value of M can be anything. Okay. Okay. So M array means it has M phase. It has M phase. So if there are M possible phases in the constellation, means for example, in a phase shifting or BPSK, remember we represented 0 and 1 here, right? So in the constellation there will be M symbol. So M symbol. Also, if we convert it to the log, then it will be converted as log base to M bit per symbol. How many bits gives this symbol depends on the number of M. So for example, M possible phases, right? M possible phases. So this is not 2. Previously in BPSK there are 2 phases. So now there are M phases. So in M array PSK, so we can write in M array PSK, we have, for example, here it was a 0 and pi phase in BPSK, right? Now in M array PSK there will be M phases. Okay, so we will have 0 twice pi by M for twice pi by M, which is 4 pi by M, this way twice pi by M minus 1 by M. So there are M possible phases. Now in a M possible phase system, for example, for ith phase, for a particular phase, for example, for phase, what should be the phase for ith phase? Nothing but twice pi I by M, where I is greater than 0, M minus 1. So here you see each one have a twice pi phase shift divided by this number m. So twice pi is, for example, this is our twice pi, yeah? 360 degree. 360 degree is divided by this m number. That's how the degree each degree is divided here. Each phases apart from each other. Okay. For example, for m equal to 2, huh? Which is what m equal to. So what should be the phases? 0. So and twice pi by 2. M equal to 2, huh? Which is actually pi. So 0 and pi. So for example, if it's m equal to 2, we are calling it BPSK, which is actually this one, BPSK. So 0 and pi. These are the two phases. So if m equal to 2, then system becomes BPSK. That's actually it's trying to say. Okay. Now in a constellation diagram, let's see how it looks like in a constellation diagram. We like to see how this BPSK, we know it's easier it this way. If it's m, how it looks like in a constellation diagram. For example, this is a for example, okay. So this is a complete constellation. For example, one of the constellation is here. For example, one of the constellation is here, or it can be here also. No, let's make it here. Another can be here, like this. Here m is of course greater than 2. Okay, so this is for what? This is for I equal to 0, means it actually corresponds to phase 0. Okay, phase 0. This is, for example, I equal to 1, and it will be have a phase, remember, twice pi by m. We don't know how many m here, for example, here could be there are 3 in each one, so here could be, here could be. So imagine we do not know the m number of yet, so we writing it m. We writing it as a name. Okay. Now for this will be the signal. Okay. So what is the phase angle here? Twice pi by m. Okay. For this one, the angle will be 4 pi by m, isn't it? From our previous formula. Okay. Like this. So this is actually I equal to 2, for example. This is for I equal to 2. This is the way. So we are saying that this is A for any signal, particular signal. So this is A, this value, this amplitude value. We know we can express any dot by its phase and amplitude. We know for particular this one, the angle is this one, and this is the yeah, angle is this one, and the amplitude is A. So if it's A, then we can clearly say that radius of this circle is A, right? Obviously. Okay, this is how in M array things are represented in a constellation diagram. Okay, so now we will see in a to a specific I point, for example, I equal to 1. Okay, or this one, let's say, let us express it in detail how any particular expression is okay, let's say here. Mm, this is an constellation. Okay, imagine this is a constellation. So this constellation for ith constellation, I could be one or whatever, this ith phase. So if this is the case, we know this is amplitude A, right? A, and its angle is twice pi I by m. Okay, if this is the case, then what should be the x value in value in x-axis? X-axis should be A cos twice pi I by m, right? So what should be in y-axis then? It's not straight. Okay, so in y-axis it would be sine twice pi I by m, isn't it? So the ith point will have projection as a cos twice pi I by m in the x-axis and a sine twice pi I by m on the y-axis. So this is the projection of this point ith point. Okay, so we can write, so the here for ith point, constellation point is what? For a cos twice pi I by m and a sine twice pi I by m. This one we termed it as a1. This one we termed it as a2. Okay. Now imagine our okay. So we will follow the same convention of the previous examples, right? So, do you remember what was our transmitted signal at any moment? Transmitted waveform or signal, xt, isn't it? We always use xt was our transmitted signal. Xt is expressed as a1 pt plus a2 pt. Very common expression. We are using this expression like again and again in and many cases. So this is a BPSK. So this mechanism M array will have lots of similarity with the PSK of BPSK modulation or demodulation in our previous examples also. Same kind of derivation will come again and again. So here P, okay, so this is P1 and this is P2. No, I made a mistake. PT. So what is the P1? We wrote it many times. Twice by T, the pulse, cos twice by FC, T, and P2. FC, T. So here the P1 and PT is given. Okay, so we can write it. T is 0 to t, also t is 0 to t. We know here where t is a by fc. Here value k equal to integer value 0, 1, 1, 2, blah, 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 up to so k by fc. Here value k 0, 1 up to m minus 1. Means actually a1 and a2 belongs to the, so we can say a1 belongs to the a cos twice by k by m, where k 0, 1, 2 up to m minus 1. This concept, and a2 belongs to a sine twice by k by m, just giving colors to highlight the point, to up to m minus 1. So a1 and a2 belongs to this constellation. Okay, now here p1 and p2, p1 and p2, they are orthonormal. So orthonormal. Remember we discussed about this two word, orthonormal. Ortho is orthogonal. P1 and P2 is orthogonal, and their normalized energy is unity. That's why it's called orthonormal. P1 and P2. We talked about this principle about P1 and P2 in our PSK and QPSK modulation previously. So if you have doubt, just go back and see our previous slides. Okay, so for the kth constellation, for the kth constellation, for kth constellation, for kth constellation, a signal which can term as a sk, we can say it belongs to, it can be expressed as a cos twice by k by m and a sine twice by k by m. Okay, so the kth constellation point can be expressed by this. What is the average symbol energy then? Average, so average symbol energy E, average symbol energy, for example, energy. So our signal was, remember what was our signal? Our signal was xt. So how can we have average energy? Nothing but minus infinity to plus infinity x square t dt. We did it like many times, right, guys? So I can write this is the expected value. So expected value of, so x square is nothing but by this equation, where we write this equation x, this one. So we'll replace this. So a1 p1 t plus a2 p2 t square dt. This one, the solution of this one, probably we did several times before also, right? So this solution will be very easier for you. For example, expected value, so it will be is a1 square p1 square t minus infinity to plus infinity dt, plus a2 square minus infinity to plus infinity a2 square t dt, plus twice a1 a2 minus infinity to plus infinity p1 t p2 t dt. Okay, so does this equation looks familiar to you guys? Okay, uh, I here I don't see this integration. Okay, now you see p1 and p2, p1 and p2, p1 and p2, they are orthogonal, so product of these two will be 0, and we know that p1, or for example, we can write it a little bit different. It will be easier. For example, it will be minus infinity to plus infinity. I took out a1 square outside, so it will be easier for you understand. You see this one? This one we did before, eh? This is the energy. We already solved it. We called it EP. EP. And this is 0 because we know this is because of the inner product of p1 p2 is 0 because they are orthogonal, right? Okay, so we say what? Orthonormal. P1 and P2 is orthonormal. They are orthogonal and their unit energy is their normalized energy is unity. So EP equal to 1, EP equal to 1. So expected value of, so it will be, our expression will be expected value of A1 square plus A2 square, right? Which is, so now A1 square, huh? Okay, so A1 and A2, where is our A1 and A2 value? Remember where I write A1 and A2? This here. A1 and A2 value is here. Okay, so I will replace it. Okay, in the next chapter, next page. So expected value of what? A1 square. So A cos y by k by m square a1 plus a2 square, so a2 a sine twice by k by m square, right? Okay, so what will happen, you see, a cos square plus sine square, so a square is outside, so expected value of a square, because cos square plus sine square is equal to 1, so it will be a square, because a is a constant value, so expected value of a constant is the same value, right? So what we find then? So we find that expected value of our signal x square t is actually a square. So here we are actually setting our symbol energy. Symbol energy is Es, for example. So a square is nothing but the Es, or A. is the square root of ES. That we get. Okay. We are not writing it EB because previously by EB we usually express EB equal to beat energy, but this is symbol energy because we are using symbol. That's why we just change the notation. Instead of EB, I'm writing ES. Okay, so how it will be in our sorry. So in a constellation, not in rice one. Okay, so this is actually A. For example, the one we are talking about, as an example. So this was our A, which has have energy ES. So what is the circle of this radius? ES. ES is also the radius of the circle. So radius of this circle is square root of ES. Energy, symbol energy. Okay. So each constellation, for example, if there are any other constellation here or here, whatever, here, they will have the same energy of ES. Now, so we know, the signal we transmitted. We know the what energy the signal was. Now say what is the receiver signal. So receive signal. Let's say receiving or receiver. Receiver for MRA PSK. How the receiver will see this signal. So what is the our standard procedure? Our receive signal is YT. You know it by heart now. So which is actually the signal was transmitted plus the noise. What kind of noise? AWGN, additive white Gaussian noise, which have a 0 mean with variance n0 by 2 blah blah blah, right? Okay. So replacing this X signal with our transmitted signal, X is nothing but A1 P1T plus A2 P2T plus this noise remains. Now, in a receiver, when we pass through this signal through a match filter, how the signal will look like, how they will appear. We know the properties of mesh filter. Each mesh to the filter mesh filter is actually in the receiver side. So response of the mesh filter is same as, like, to have a maximum SNR should be the equivalent to the response of the pulse shaping generator. Okay. Okay. So this pulse will match filtered with response H1T P1 equal to P1 T minus T, and also it will be matched because there are two distinct pulses here, P1 and P2. So we will have to use two distinct match filter response. We have seen it previously also. So this match filter will have H2 T P2 T minus T. If this is the case, then for A1 PT, we will have, I'm not deriving this detail of this equation because we already did it. So the for A1 PT, we will have A1 EP EP plus N tilde, because this you see this noise is additive. This noise is actually already added to the both parameter, this parameter and with this parameter. When it will pass through the match filter, each match filter, then the noise changes. So this change amount is actually denoted by N tilde. Same thing, it will be a 2 EP plus N2. Okay, give it a name, N1 tilde, N2 tilde. Okay, let us give it a name. This is R1T. Usually, after the match filter, we give it to RT, but here we have two components, so we give it our R1T and R2T. This T is the sampling interval T. Okay, so R actually is a combination of R1T and R2T. That's all actually. Okay. Now we will see how these are 1T. So you see R1T and R2T, they are actually in the receiver side. So let's say how the constellation point we can find them. For example, let's draw it here. Let's draw it. Okay, it's not a nice circle. Let's assume it's a nice one. This is the best one I can do. Okay, so let me draw some constellation point. Imagine here is a constellation point. Here is a constellation point. There is a constellation point. Okay. Yeah, three constellation point. Probably in when we started our example, we draw the three constellation point because it's M, so you can do it own way, no problem. Okay, so this was our term. This was, for example, imagine this was our transmitted symbol. This one, which is yeah, transmitted symbol. This transmitted symbol, this constellation is dictated by. Remember what was our equation? A was ES, A cos twice pi k by M, ES sine twice pi k by M. Remember this constellation which we transmitted is dictated by this constellation coordinates. Now imagine we received this constellation not exactly here because there are noise and it was transmitted blah, blah, blah. So we imagine we received this constellation here. Okay, this was his ideal place, but instead of here we placed it here, which is actually RT. This is the receive signal. This one R1 RT is nothing but the combination of, which is actually a function of the R1T and R2T. R2T. We received it here. Now, so how to find it? How to find it, this constellation point? How we take the decision? So you see, if so, there is a dilemma here. When we receive the signal here, the signal was originally transmitted here. Now, we have to take a decision whether this constellation was here, whether this constellation will be here, whether it's going to be here. Okay, so we had to take a decision. Okay, so the question is based on what? We transmitted a signal. We ideally it was here, but we received it here. So how to map it? You can say remapped it. Means there must be a decision rule. What is the decision rule? Okay, let's say. So what is the decision rule? Decision. How this decision will be dictated. So one thing is very like common sense is the distance. If the one this constellation, the distance uh, like shortest distance will be the, or we can say minimum distance. Okay, so our decision rule should be dictated by the minimum distance. So minimum distance. So what does it mean? That okay, you received a constellation here. So what is the minimum distance to the closest constellation? Okay, most likely this is the closest distance because this distance or this distance is higher than this distance, right? So this is the decision rule. The minimum distance will be the targeted constellation. Okay, so minimum distance or nearest constellation. We can also say or nearest constellation point. Constellation point from our this receive signal, from receive signal RT. So that point will be the original transmitted point. That is how you will find it. So we actually set a standard that how to find a constellation point. We find that okay, our constellation point will be minimum distance or the nearest constellation. Okay, so what was our signal? Remember our signal or k signal was sk. So that is actually our signal, which is actually the kth point of mRNA signal. mRNA PSK. This is our PSK signal. So how to find it? Okay, what is the minimum distance then? The minimum distance is this RT. RT. This was transmitted signal. So this is higher distance. Any distance will be, then the ideal distance will be the higher distance. So RT minus SK. So RT minus SK distance, that should be a minimum for K or K symbol. If this distance is minimum for any point, that will be our original transmitted constellation. So what I am trying to say is choose constellation point, choose a constellation point such that distance is minimum. Distance is minimum. Very common sense. So for our receive signal, which one you should choose? Is it minimum? No. Is that minimum? No. Is that minimum? Yes. So that will be our receive constellation. That actually is trying to say with all stuff. Okay. So what is the minimum distance then? Okay, for that, let me write our RT signal. Which is, if you know 2 points, what is the minimum distance between them? That's actually the uh, trick here. So RT is a value depend on R1 and R2, and SK is nothing but the ES, which is A cos twice by k by m and es sine twice by k by m. So we want to find the distance, minimum distance between, this is the transmitted constellation, this is this is the transmitted constellation, and this is actually our received constellation. What is the minimum distance between them? How to find it? Simple math. How to find the minimum distance, right? The minimum distance point. So for minimum k, the distance would be nothing but r1 t. So r1t minus es cos twice by k by m square plus r2 t minus es sine twice by k by m square and square root of this minimum k for minimum k. That is actually our minimum distance. So that is the distance. That is the distance, or distance minimum, or minimum distance. Minimum distance. We know this is the minimum distance. How to quantify it? So this is the way we will quantify it. Okay, so this is the minimum distance, or you can quantify the minimum distance. So we have this decision. So uh, so our decision rule is finalized. How to decide it and how to quantify it. What remains then? Remember our usual approach, how we simulate a something. How you do that? We transmit a signal, we receive a signal, we find the receiver signal like RT. We have a decision rule. Then what is the next point? Error, probability of error. How we find that, because this is signal, so how to find a probability of error, that remains. So what is the error? So M array PSK bit error rate. How to find the bit error? This is actually a standard procedure. We always follow the same steps again and again for every schemes. Now, for bit error rate for PSK, especially for M array, it's not like the way we did it traditionally. In traditional way, we cannot solve this this expression accurately. So we will employ an indirect approach. So because it's not easy to find that, we'll employ an indirect approach. So we will find a kind of approximate approximate error. Okay, for that, let me give you an example which will help us to find M array. What is the simplest form of M array? Previously, remember? QPSK. In QPSK, we have 4 constellation. In M array, there are M number of constellation. Okay. Instead of making it complex, let's go back for a QPSK constellation. Okay. For QPSK constellation, each one has a value. If you remember, it was termed as beta rate, EB, square root of EB. It was constellation as EB minus EB, minus EB, minus EB. This is minus EB plus EB. So remember, in QPSK we transmitted 00011011. That I'm actually trying to map here. That's all. Okay, now for this each constellation, for example, there are two uh, nearest neighbor. One is this one is this nearest neighbor, and another is nearest. So who is our targeted? This is actually our targeted constellation. From this constellation, there are two neighbors constellation, right? So each constellation has a two nearest neighbor. Okay, that I'm trying to say. Or if this is the case, then we are say that okay, alpha equal to 2. Just give it in notation, that alpha equal to 2, which express that each constellation has two nearest neighbors. Okay, from there to choose actually. So what is the d minimum, or distance between minimum, is nothing but 2 of the square root of eb, right? Is the d minimum distance. So now we will be using the same example or same strategy that we used in QPSK. So QPSK is the most simpler version. So if this is the true for QPSK, which will also be true for our M array PSK. Okay, if this is the case for approximate symbol error rate, or SER, symbol error rate, because they are symbol, there are two bits makes a symbol. So this is symbol error rate will be, for this case QPSK, alpha, which is two nearest neighbor, Q function d minimum by twice n0. So the minimum is the distance to the nearest neighbor. Okay, so it's actually nearest neighbor expression. So why we want to use it, nearest neighbor expression? This simple mechanism is very much useful for expression of a very like complex system, or to find the uh, bit error or symbol error in a digital communication system. So the same mechanism can be used for any other cases. For our case, we will be using it for our MRA MRA PSK system, the same stuff, right? So for our cases, let us redraw the whole mechanism. We draw it earlier. I will draw it. So let us draw this one again, nicely with big picture. Okay, let's say no, it's not a good circle. Okay, just kind of circle. Okay, assume it's a good one. Okay, so for our case, we will take a constellation here, for example, which has an energy Es, which is also the radius of the circle. Okay, now imagine our targeted value is here at 0. Just simplify. So k equal to 0. Okay, so how to make the angle then? So this angle will be what? This angle will be twice. So this angle will be twice pi by m. Okay, if is k equal to 0, then this angle will be twice pi by m. Now this is the nearest distance. This is the nearest distance. If it's a nearest distance, then what is okay? So this is our targeted one. Remember, this is the targeted one. This point 0 degree. Now, because it's here, there could be another constellation here. Constellation is everywhere. There are here, there are here. Okay, so we are looking for the nearest one. So this is also a nearest one. For this guy, this is also nearest one. This is also nearest one. So we'll just took one of them. Then it could be easier for us to understand. Okay. So how to find it? Geometry. Okay. So we will find the midpoint of these two distance connected. It becomes the 90 degree now. So what is this angle then? This angle will be uh, twice pi by m divided by 2. So pi by m, right? This is half of this distance, pi by m. So no 2, no 2. So it's twice pi by m. So half of this distance is pi by m. That is the angle. Okay. So what is this half distance? So half distance, we can write d minimum, d minimum by 2. This is actually our minimum distance. This is our d minimum, and this one is a d minimum by 2. What is the mean by 2? It's nothing but es by sine pi by m. Okay, because this is 90 degree, this is 90 degree, this is 90 degree. So you know this is the dm by 2. This is our approximate of es. Actually es was up to this point, but we approximate because this is approximation. So we assume that okay, this up to this point is also like here to here. This also up to es, though theoretically up to this point is the es, but we are approximating. So the minimum will be twice of square root es sine pi by m. Okay, so we know the minimum distance, right? So now each point has how many nearest neighbor? So this was our targeted constellation, and this is one is the nearest. This is also a nearest. So what is up? So nearest neighbor, neighbor alpha equal to 2, right? So what is the error? You see how we find the, if it's a symbol error rate by this formula. So by the same, so probability of error is probability of error, how much? Alpha is 2, alpha is 2 because nearest neighbor is 2, q d minimum, right? What is the formula? D minimum by 2 I sin 0 by 2. So we can write d minimum is nothing but 2 square root of es sine pi by m. Yani okay, sine pi by m by twice n0. So this is actually our probability of error or symbol error rate. Okay, just little bit simplifying. So twice es sine square pi by m by n0. So this is actually our approximate probability of error or symbol error rate. So this is our actually our approximate symbol error rate for M array PSK. For high value of ES by N0, this approximation will be correct or more correct. Higher the value of ES by, like ES by N0, at this value, higher the approximation will be more accurate. So we did all the steps. Then we find also the error rate for M array PSK system. So we will stop now.